So let's try the easier one. X1 plus x2 greater equal to 1. Easier because, it's got simple coefficients, but there's a little bit of a twist. It's greater equal to 1. Doesn't matter, right? Doesn't matter. So we still change it to an equation form because the equation form creates a line on the graphical space. Okay, so we are going to basically then do that and just give me a little bit of a time to make sure it doesn't jitter so much. Okay, all right, thank you. All right, so when we have an equation, we want to draw a line. Just now it was easy, just x1 equals to 8, x2 equals to 6. With this case and the more generic case, when we have non-zero or non-unity coefficients, right now it's unity, right? It's 1 times x1 plus 1 times x2. So it's also easy, but it's as simple as basically just substituting, finding two convenient points on the graphical space so that we can join the 2 points together to form the line. And what's more convenient than to first assume x1 is 0, therefore x2 is 1, right? So x1 is 0, therefore x2 is 1. We have 1 point. Then we assume x2 is 0, therefore x1 is 1. So x2 is 0 on this x-axis, x1 is 1. We have another point. So with 2 points, we can then feel free to join up the 2 points on the graphical space, all right, and we get one additional vertex. We kind of cut away one vertex, one corner, and create 2 vertices, thereby creating one net additional vertex. So we have now 1, 2, 3, 4, 5, 5 corners due to 5 constraints being drawn. Yeah. But wait, we still need to decide, should we discard the now top, bottom, left, right? Don't make much sense now, right? So let's say the northeast region and the southwest region. Which one should we discard? Now, don't let your intuition or subjectivity take over. Oh, it must be that we want the bigger region. There's no such law or no such understanding at all right? It may be that the truth of the question requires us to retain the small region. So how do we know? Well, here is where we use a litmus test. Pick a point in any of the regions, all right? I'll pick from the smaller region. Pick one point and substitute it and see if it satisfies the original constraint or not. If it does, then it is the region we want. Otherwise, we discard that. So one convenient point that I always use, and I think you're going to like it, is the point 0, 0. It's so easy, right? To plug it in and find that left side adds up to 0. 0 is not greater equal to 1, so we are going to discard the entire triangle here. All right, because you can always check, is 8, 0 what we want? You plug it in, 8 plus 0 is 8, greater equal to 1, so yes, the entire region is what we want. So you can pick any point, even fractions, but why make life so difficult, right? So if we plug in 0, 0, this always works, unless you have x2 equals to x1, the line through the origin with gradient 1, then we have trouble. But other than that, it's quite okay. So we plug in and we really don't want this little triangular portions. We kind of chip it off, all right? And then we are left with a 5-corner polygon. And we just have one more equation to go. Do you want to go ahead and get started? Yep, okay. First step, remember, change it to equation form, right? So 3x1 plus 4x2 equals to 36. So with this, we need 2 points. Yeah, of course, you know why I have picked 36, right? Because it's easy to do division mentally. let's pick x2 equals to 0 and x1 equals to 12. So that means we have 11, 12 over here. All right, x2 is 12, x1 is 12, x2 is 0. When x1 is 0, x2 is 9. 36 divided by 4. So we have here. So we have now 2 points, and we can feel free to join them up like this. All right. Cutting off an old corner, creating 2 new corners. All right, thereby adding 1 net additional corner. So we now have 1, 2, 3, 4, 5, 6 corners due to 6 constraints. Just to validate our understanding again. Yeah. So we have to decide which part, all right, or which partition should we keep or throw away. Remember the litmus test point, our favorite point, 0, 0. Now you might say, but wait, 0, 0 has been discarded. Can we still use it? Can, because we are considering this line momentarily. So it is as if the rest of the lines don't exist. So 0, 0 is still in our game. So we can consider, should we keep 0, 0? And when we plug it in, 0 plus 0 is less than or equal to 36. Oh, okay. So we are going to keep the lower left side and discard the upper right side induced by this constraint. And that's it. We are done. All right. So this is exactly our constraint, our feasible region. Let's make it a little bit bolder so that it stands out a little bit clearer. All right, so as you can recall, it is not difficult at all. And in fact, for the numerical separations, so long as you can more or less make them uniform, you notice that our diagram ends up pretty okay. Yeah, but of course, what you want to do is to make sure that your polygon is big enough so that it is when you hand it in as homework exercise or as exam solutions, it will be clearly legible. Now, I've seen students starting with very squeezed axes. So 1 and 2, 2 and 3, 3 and 4 are all compressed together. You will have problem later on because you cannot tell the corners apart, and that will be a problem. Yeah. Okay, what will happen next is that we need to find out where will be the optimal solution, remember? Okay, now we need a law here, and because it is law of mathematics, law, everybody must obey. All right, and this law states that optimal solution or solutions, as we'll see, there may be more than one. If they exist, all lie at the corners of feasible region. Okay. Now, the corner makes no sense if you don't draw a picture of it. So that is thanks to our understanding using graphical solutioning approach that we can understand. Oh, corner, yeah, that just means, you know, these points here, right? Yeah, so if we just open the textbook without pictures, without graphs, without talking about graphical solution, and we see this very, very important law of linear programming that tells us exactly where to look for optimal solution, we'll be totally lost, because what do you mean by corner? Corner in what sense, right? In the abstract algebra sense, how do I understand or even see it? Well, it becomes very visible and easy to understand because corners just mean this, right? So let's understand this again. Optimal solution, the best part. Remember, the best combination of tables and chairs uh, lies, if there's only one solution, then it must be at the corner. If there are multiple solutions, then it still has to be at the corner of feasible region. Yeah. So let's just assume, which is true, that there is only one optimal solution in our sample problem here. Well, now, if we don't use law of linear programming, then what do we have? We have to explore each and every interior point, right? And evaluate them. And even if you're using computer, how many points are there? Well, that's infinitely many of them. Yeah. So there are many decimal places uh in presenting themselves as possible solutions. So if you evaluate each and every point and combinations of them for x1 and x2, it is just no way to get a solution in in feasible time, in human time, right? For even just a simple problem like this, not to mention a 2000 variable problem. So it lies at the edge or lies at the corner of the feasible region. Well, corner in a way can be the edge here, and the corner of the line at the edge is the corner here, right? So in long story short, it is at the corners. Now we just need to find out what are the coordinates of the corners. Let's begin with the easier points. We know that this is already 8, 0. Okay. And uh, we also know that this is 1, 0 by construction. We know that this is also by construction 0, 1. So these are the easier ones. This is by construction 0, 6. And it remains to find out what are these 2 points, right? Yeah. So that gets us back to simultaneous equations. Fortunately, this time we have 2 constrained boundary lines, right, intersecting. So there's always a solution, and we just need to substitute in the relevant uh, what do you call it? Equations, not inequality equations. So for example, this line was a result of 3x1 plus 4x2 equals to 36. I kind of write it at the side here just to remind us so that it doesn't get messed up in the whole picture, right? So, and this is a result of x1 equals to 8. So very simply, we can solve for these two, and we observe that x1 is 8. Substitute in, we get 3 times 8, 24. All right, 24. Well, where should I write? By the side here, just a side working. 24 plus 4 times x2 equals to 36. Yeah. So x2 equals to 36 minus 24, 12 divided by 4, we get 3. So in other words, 8, 3. 8, 1, 2, 3 is our solution point. 8, 3. Intersection point here. Okay. And finally, we have this. This is a result of 3x1 plus 4x2 equals to 36, and intersecting with this line, which is easy, x2 equals to 6. So again, we can substitute in x2 equals to 6, right? We get 4 times 6, 24. So we don't know x1 plus 24 equals to 36. And this means that 36 minus 12, 24, we get 12. 12 divided by 3, we get 4. So x1 equals to 4. Which means that this point, which is kind of already very obvious, it's lying around x1 equals to 4. And of course, the slight deviation is just due to my inaccurate drawing. So 4, 6 is the coordinate of this intersection point. Now, it remains to ask which point is the best out of all the corners, because thanks to law of linear programming, we didn't have to look at all the interior points nor the points along the lines. Just looking at the intersection of the lines will do, right? The